A symmetric I section with the width of the flange equal to 50, thickness of each flange equal to 10 mm, depth of the web is equal to 100, thickness of the web equal to 10 mm of a steel is subjected to a shear force of 100 kN. Find the magnitude of the shear stress in Newton per mm square in the web at its junction with the top flange. So this figure represents here the symmetrical I section, and the width of the flange is 50 mm and the depth is equal to 10 mm for the web. The depth of the web is D2 equal to 100 mm and the width B2 equal to 10 mm. Because of a symmetrical section here, we can locate the neutral axis. Neutral axis is a distance equal to 50 mm from B. So position B from neutral axis is D2 by 2, that equal to 50 mm. We are interested to know the shear stress at section C, and C is in the web. To find out the shear stress at C, we'll take the FBD above the section CC. So we'll get this rectangle here AB, and this one is same as section CC. At this corresponding point here, we have width of the section CC is equal to B, and this B is same as equal to B2, and we have B2 equal to 10 mm. The shear stress is calculated as V multiplied by area multiplied by Y bar divided by I divided by width B. Out of that, width is equal to B2. Now for this section, you have to take the area as a B1 multiplied by D1. So in this case, we have area is equal to B1 multiplied by D1. We have width is equal to 50 and depth equal to 10. That equal to 500 mm square. Then you have to locate the centroid of this section G2, which is D1 by 2, and you have to measure this height from the neutral axis. So this centroid you have to locate here. That centroid will be distance equal to 5 plus 50. So in this case, we have Y bar will be equal to 10 divided by 2 plus we have D2 by 2, that is same as equal to 50. So in this case, you will get Y bar is equal to 55 mm. In addition to that, we require the moment of inertia. Moment of inertia we can find out by taking the rectangle of size equal to 50 plus 10 plus 100 plus 10. So outer rectangle will take and will subtract the two rectangle. Already we have done this in the case of bending stress. So moment of inertia of the I section will be the outer rectangle here. Outer rectangle has a width equal to 50. So that will be our B1, and the total depth will be D is equal to 10 plus 100 plus 10, that equal to 120. For this rectangle here and this rectangle here, the total width will be equal to 50 minus 10. So this width will be equal to 50 minus 10, that equal to 40. So this much moment of inertia to subtract from the largest rectangle, and the height of this one is same as equal to 100 mm. Moment of inertia of a symmetrical I section is same as equal to the moment of inertia of a larger rectangle, which is same as equal to 50 multiplied by 120 cube of it and is divided by 12, minus moment of this rectangle, which has a width equal to 40, depth is equal to 100, cube of it, and we have divided by 12. In this fashion, we can very quickly calculate the moment of inertia of the symmetrical I section. This value come out to be 3.86 into 10 to the power 6. That will be mm to the power 4. So almost everything is ready here, and we have shear force is equal to 100 kilonewton. So let's calculate here shear stress at CC. So we have shear force is equal to 100 kilonewton is 100. Kilonewton is 10 to the power 3. Area is equal to 500. Y bar is equal to 55. Divided by moment of inertia is 3.86 into 10 to the power 6. And width B2 you have to take is equal to 10. So shear stress at section CC is come out to be 71 megapascal. The given figure, all dimensions are in mm, and we have given here the symmetrical I section of the beam. The shear stress at point P very close to the bottom of the flange, that is close to the bottom of the flange is 15 megapascal, and the stress at point Q, which is very close to the flange. When we shift from P to Q, there is a sudden change in the shear stress. So we have shear stress at point Q divided by shear stress at point P is inversely proportional to their width. So therefore this ratio is the width at P divided by width at Q. Shear stress at point Q you have to calculate. So we have shear stress at Q equal to width at point P is equal to 100. Width at section Q is equal to 25. This value is cross multiplied and the shear stress at P is equal to 15. 100 by 25 is 4. 4 into 15 is equal to 60. Shear stress at point Q is equal to 60 megapascal. A beam is of square section with diagonals of 40 mm long and a horizontal as shown in figure. If the shear force at a particular section is 15 kN, what will be the shear stress at the layer AB? You have to find out. To find out the shear stress at the layer AB, we have to first fix up our neutral axis, that equal to the same as the horizontal diagonal. Then you have to measure the vertical distance here, that will be same as equal to y. Then you have to hash this area. Once you hash this area, you have to find out the centroid of this area and the area of this area, that is ACB. You can calculate the shear stress on the fiber AB. Shear force multiplied by area ACB or ABC multiplied by y bar for this area divided by I and divided by the width. This time the width is same as equal to AB. So you have to find out the width B. To find out the width AB is here, we'll find here triangle ACB and the triangle DCE are the symmetrical triangle. This triangle is a larger triangle, is triangle DCE. It has a base equal to 40 and it has a height equal to 40 by 2, that equal to 20 mm. So D represent here the horizontal diagonal, that will be same as equal to 40 mm. And the height of the triangle will be 40 by 2, that equal to 20 mm. Here we can locate the fiber AB at a distance equal to 10 mm from DE. The fiber AB is at a vertical distance equal to 10 mm. It means that the remaining distance is also equal to 20 minus 10, that equal to 10 mm. So we'll continue with this figure and this formula and we'll calculate here the area of the triangle ABC. For this one you again will use the property of a similar triangle and we can find out AB because AB is proportional to DE. Height is already known to us, so the area is known. So in this one is so we can locate the centroid of triangle ACB. From base it will be D by 3 and from apex it will be 2D by 3, where D will be equal to 10 mm and the width is same as equal to AB. So here the triangle DCE is similar to triangle ACB. Triangle DCE is symmetrical to triangle ACB. This is useful information for us to find out the width at distance equal to 5 from the neutral axis NA. So in this case we have AB divided by DC is same as equal to the vertical height for this triangle is 10 mm and for larger triangle it will be equal to 20 mm. So in this case we'll get AB is same as our width B will be equal to 1 by 2 and we have DC is equal to 40. So we have width is equal to 20 mm. Next we have to calculate what is the area of the triangle ACB. So this time the height is known and the base AB is also known. So we can very well calculate the area of this triangle. So we have area of the triangle ABC is same as equal to 1 by 2. We have base AB is equal to 20 and the height is equal to 10. 200 by 2, that equal to 100 mm square. Then we have to locate the centroid here. So centroid of this triangle will be G1 and this distance will be same as equal to 10 by 3. That is D by 3. D by 3 is same as 10 by 3. And the total distance from the neutral axis will be equal to y bar. So from neutral axis we have centroid of the triangle ABC is equal to This distance is 10 plus 10 by 3. So we have 10 plus 10 by 3. That is equal to 40 divided by 3. 40 divided by 3 is same as 13.33. That will be mm. We know the shear force is equal to 15, area is known, y bar is known, width is known. One more thing we required is moment of inertia. The moment of inertia of rhombus is given as the side of the square to the power 4 divided by 12. Side we don't know. Since here the diagonal is equal to 40 mm, so half of it will be equal to 20 mm, as well as this diagonal is equal to 40 mm, that will be half of it will be equal to 20 mm. So vertical side here is 20, horizontal is 20, so we can find out the dimension A. So dimension A will be same as under root of 20 square plus 20 square. So we have 20 square plus 20 square. That is we have 20 root 2. 20 root 2 is same as equal to 28.28. That will be mm. So the shear stress at the fiber AB will be equal to, we have shear force is V, that equal to 15 kilonewton, that will be equal to 15,000 Newton. Area is equal to 100 mm square. Y bar is equal to 13.33 is divided by moment of inertia of a rhombus is same as a to the power 4 by 12. So in this case we have 28.28. Power is 4 divided by 12 will shift in numerator and divided by width. Width at section AB is equal to 20. So solve this, you will get the shear stress at the fiber AB. In this case we'll get the shear stress at the fiber AB is approximately equal to 18.75 megapascal. A bending moment at location X in a rectangular section beam, cross-sectional area equal to 3600 mm square is given as m equal to 12x minus 3x square for a limit of 0 to 4 meter. It means that we have length of the beam is equal to 4 meter. The maximum transverse shear stress in megapascal in the beam we have to calculate at x equal to 1 meter. In the case of rectangular section, the maximum value of a transverse shear tau max is same as equal to 3 by 2 of average shear stress. Average shear stress is same as V divided by area. Area is already given to us is 3600 mm square. Shear force you have to find out. For that one he has given the value of m equal to 12x minus 3x square. In the beginning we already developed the equation for the shear force. Shear force is given as the derivative of m with respect to x. So this equation will give you the shear force at any distance x. So we have shear stress at any distance x is same as equal to derivative of m. So derivative of 12x will be same as equal to 12. Derivative of 3x square will be equal to minus 6x. We are interested to know the shear stress at x equal to 1 meter. So at x equal to 1 meter, we have shears equal to 12 minus 6, that will be kilonewton. That is same as equal to 6 kilonewton. So we'll substitute this value here. We have 3 by 2. Shear force is equal to 6000, that will be Newton, and the area equal to 3600. So in this case the maximum shear will come out to be 2.5 megapascal. Consider a simply supported beam of length equal to 50 h with a rectangular cross section of depth equal to h and the width is equal to 2h. The beam carries a vertical point load P at its midpoint. The ratio of the maximum shear stress to maximum bending stress we have to find out. In the flexure formula, the maximum bending stress will be same as equal to the maximum bending moment, that equal to maximum value of a bending moment. For rectangular section, the top fiber and bottom fiber at the same distance equal to d by 2 divided by the moment of inertia of a rectangular section. And the maximum value of a shear stress, that equal to tau max, will be equal to the maximum value of the shear force in the given section. That is why I use the here V max. Actually V max is same as equal to V divided by the area A. and this one is the average value of a shear is to be multiplied by 3 by 2. That will be the value of maximum shear. So first you have to identify, in a case of simply supported beam, if we have a center load, where will we have maximum value of bending moment and where we have maximum value of the shear force. So consider here a simply supported beam. We have support at A and B and we have central load is equal to F, exactly placed at the midway. So the distance from each support will be equal to L by 2. So in this case, because of symmetrical loading, the reaction at A will be equal to F by 2 and at B is also equal to F by 2. So we'll get here one rectangle in the case of shear force, that will the positive value is F by 2, and second rectangle we'll get is a negative rectangle of height equal to F by 2. So the shear force diagram will get here one rectangle, this value is same as equal to our F by 2. There is no load is acting between A to C, the shear force is remain constant. The shear force is equal to F by 2 and we have A to C is same as equal to L by 2. So in this case the maximum shear force will be F by 2 and the height here will be equal to minus F by 2. This distance is also equal to L by 2. So this one is the positive value of a shear force, this one is the negative value of a shear force. Shear force before the section C will be positive value and after the section C is a negative value. It means that the shear force changes the sign at point C. In that case, the maximum bending moment will occur at point C and the maximum value of a shear force will be same as equal to F by 2. And the maximum bending moment at point C we can calculate as area under the shear force diagram. In this case, we have maximum value of bending moment M max will be equal to area under the shear force diagram is same as F by 2 multiplied by L by 2, that equal to F into L by 4. And the maximum value of a shear force is V max, that will be equal to F by 2. Either you can take this height or you can take this height. So this is same as our regular shear force equal to V. So maximum shear will be equal to V is same as F by 2 and the maximum bending moment is equal to FL by 4. For rectangular section of width B and the depth D, we have shown here the shear stress. Shear stress is maximum at the neutral axis is 3 by 2 of the average value of a shear stress, that equal to F by 2. And the maximum value of a bending stress will occur on the top fiber and the top fiber here at distance equal to D by 2. He says that we have a depth is equal to H. So we have to take the value of D is equal to H. The value of B we have to take is equal to 2 times of H. So this figure is not to the scale. And secondly, he says that the length L will be equal to 50 times of H. So here we have to take the length L is equal to 50 times of H. So maximum bending stress will occur at distance equal to C and we have C is equal to, so that will be same as H by 2. Total depth equal to H, so maximum fiber will be at distance equal to H by 2. So let's calculate here the maximum value of a bending stress. So we have maximum value of a bending stress is equal to FL by 4. So first of all I will write in a standard form. We have FL by 4. Then we have distance C. C is same as equal to H by 2. So we have H by 2 divided by I. I is equal to BD cube by 12. So we have B is equal to 2H. Depth equal to H, so we have cube of it and 12 will shift in numerator. So we'll get this value is equal to, this is 12 and 4, so that will be equal to 3 by 2 multiplied by F. We have L is equal to 50 times of H. One of the H will be get cancel here and in the denominator we have H square. So we have 3 into 50 is 150, 150 divided by 4, that will be equal to 37.5. So maximum bending stress is 37.5 times F divided by H and square of it. Similarly, we can calculate here the maximum shear stress. Maximum shear stress will be tau max. This time we have maximum value of a shear force is equal to F by 2. So we have F by 2 and divided by area. So it is equal to 1 divided by area is equal to 2H multiplied by H is 2H square and is further multiplied by 3 by 2. So we have 3 divided by 2. Again we'll get here this time 3 divided by 8. 3 divided by 8 is same as 0.375 multiplied by f divided by s square. So independently we have calculated the value of sigma max and tau max, and now we are interested in the ratio of maximum shear to maximum bending stress. The ratio of the maximum shear to the maximum bending you have to calculate is a tau max by sigma b max you have to calculate. Tau max is 0.375 f by s square, so f by s square is get cancelled, and we have tau max equal to 0.375 divided by sigma bending maximum equal to 37.5. So this answer is very close to 0.01. It means that the magnitude of the shear stress is negligible as compared to bending stress. Choice D is correct choice. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.